Last time I talked about the volume in high dimensions, so in particular volume of balls. I'd like to understand concentration phenomena. So this means we are looking, let's say, on a ball, maybe let's say the unit ball. And we measure the size of it by its volume. Okay, but because we want to compare volumes of sets with given properties with this one, I mean, we want to talk about probabilities that something happens. So this means we normalize the unit ball, let's say, to probability 1, and then we are looking on properties of sets there, and we want to see that maybe with very high probability something happens. So those are the concentration phenomena, and I already gave the slogans. So in high dimensions, in a ball, the mass concentrates essentially at the surface, and it also concentrates essentially at any equator, and I have two vectors, they are essentially orthogonal. Okay, and I want now to make those statements more precise, because we really want to have precise statements, estimates, which tell us that those are really concentrating. Good, okay, so let us go through these three slogans. So the first was that the volume of the ball is concentrated close to its surface. So let us look on, first of all, what does this mean and how do we really prove this in a rigorous way. So the slogan 1 was let me write it again. So the volume of the ball is concentrated close to its surface. And of course, in small dimensions, this is not true. This is really something which happens in large dimensions. In small dimensions, if I'm looking at the disk, of course, the mass is spread out over the disk. And if I take a small slice around the circle, there is not so much. But in higher dimensions, there will be more and more sitting there. Good, okay, but so how do I really prove this? Or what is a precise statement? Okay, so, I mean, I'm saying close to the surface. Of course, the surface itself is a lower dimensional object, so this doesn't have any mass. Okay, so I really have to take a small neighborhood of the surface, and so we take an epsilon neighborhood. So we're looking on things which are epsilon close to the surface. Okay, so let us fix this. Epsilon, so can be small. Okay, then we have for our vectors, and now I address them as random vectors because I mean I'm looking on their probability. I mean I'm looking on all vectors in a unit ball, but I consider this as a probability space where the probability of sets is measured by the size. Okay, so that's I'm talking about random vectors, and of course we look on the probability, which in this case of course is just the ratio of volumes. Okay, so then we have for the random vectors, so our vectors in the unit ball, the following statement, or at least, I mean, what do we want to calculate? We want to calculate the probability, let's say, that the norm of my vector is close to the surface. So the surface, of course, is the vectors, the points where the norm is equal to 1. So the norm here is a 2 norm, the Euclidean norm. Okay, the length of a vector. Okay, if I'm close to the surface, it should have norm, let's say, bigger than 1 minus epsilon. So it should be close to 1. So that's what I really want to see, that this is getting larger and larger in high dimensions. Okay, and I mean the P here, of course, this now stands for probability. So we make probabilistic statements, but I mean the probability I'm measuring here is essentially the size of the set with the given probability compared with the size of the whole space which I consider. The whole space is here the unit ball. So this here really is the volume of exactly the set of vectors which has this property. So it's the volume of the vectors in the unit ball for which the norm is bigger than 1 minus epsilon. And for probability, I should normalize things, so I'm normalizing this with the volume of the whole unit ball. Okay, so if I consider all my vector in a unit ball. This set has probability 1. That's just everything. And then, okay, I take the ratio which have this property. And of course, yeah, I mean, I can also write this. So essentially, I want to see that this probability should be close to 1. I mean, saying that most of them have this property, this means this probability should be close to 1. And maybe for this, it's good, instead of saying this is big, maybe if I go here the other way, then I should say this is small. Okay, so I can also write the volume of the vectors which have lengths bigger than 1 minus epsilon. This is of course the same as all vectors minus the ones which have lengths smaller than 1 minus epsilon. So this is the volume of the unit ball minus the volume of the vectors which don't have this property. And those are of course the vectors which have lengths smaller than 1 minus epsilon. So that's the vectors on the inside. Okay, and of course still dividing by the volume of the whole unit ball. And now of course you see, I mean this here is 1 minus this. Okay. So yeah, this is 1 minus, and then I'm left with the volume of the elements in the unit ball which have norm less or equal 1 minus epsilon divided by the volume of the unit ball. Okay, and now probably you see why it is good to go over from bigger than 1 minus epsilon to less or equal to 1 minus epsilon, because this now of course is just again a ball, but a ball of radius 1 minus epsilon, and we know what the volume is. So we just can use the formula which we have. So what I have here is 1 minus, and this here, so those are the guys in a unit ball which have lengths less than 1 minus epsilon, but of course those are just the vectors which are in a unit ball of radius 1 minus epsilon, or square root of 1 minus epsilon, yeah. Okay, so this is 1 minus, so it's the volume. No, that 1 minus epsilon is the radius. Okay, so it's the volume of the ball of radius 1 minus epsilon divided by the volume of the unit ball, and maybe let me write it explicitly, radius 1. So we just have to compare the volume of radius 1 with the volume of 1 minus epsilon, but we have explicit formulas, and the only thing which matters here is how it depends on the radius, because I mean we have coefficients, pi and the gamma function, but those are the same for those. So they cancel away, and so we just get here the ratio of how things depend on the radius. So we have 1 minus, and the dependence on the radius was of course the radius to the power p. So here I get 1 minus epsilon to the power p. Okay, and here I just get 1. And the pi factors and the gamma functions, I mean, they are the same for both, because I'm in the same dimension here. Okay, so the dimension is showing up here. And now, of course, we see that if now p goes to infinity, this guy here goes to 0. Okay, so that's the idea. I mean, I'm fixing epsilon, so epsilon is fixed, and then p goes to infinity. 1 minus epsilon is a number smaller than 1, can be close to 1, but it's smaller than 1. So if I take a power of this will go to 0. So this goes to 0, and then this here converges to 1. So this is, of course, for p going to infinity and epsilon fixed. Of course, you always have to think, I mean, what do I want to keep fixed and what do I vary? So, but in such estimates, usually you fix the epsilon, how close you want to be, and then you make the dimension bigger. So this is if epsilon is fixed. Yeah, so this goes to 0. Okay, but of course, often you also want to see this in this way, that of course, I mean, if epsilon is fixed, then you will have less and less mass in the shell outside of this. But of course, if the dimension goes higher, you can also scale epsilon with p, and then you can ask, yeah, so how should I scale it that more or less I have the same kind of mass sitting in this shell, which is getting thinner and thinner. And of course, I mean, this formula here essentially also tells us how we should do this. So namely, we should here scale epsilon. Yeah, with what? I mean, what? In order to get here something which doesn't go to 0, but maybe has a finite limit. So how should I choose epsilon? Yeah. Yeah. 1 over p, because then I get essentially an approximation of E. Okay, so this formula tells me I should choose epsilon as 1 over p, or maybe a constant by p, but it should go like 1 over p. Yeah, so let me write this down. So if one wants to keep the volume in this slice, in this skin of my ball, or of my apple, or whatever, kind of a constant, if p goes to infinity, or for big p, one should scale the epsilon also with p. One has to scale epsilon with p. Okay, and this formula, which we have very explicitly here, suggests that we should scale epsilon, let's say like 1 over p. Because then, yeah, what do we get then? Then we have the probability that the norm of x is bigger than 1, and now the epsilon is 1 over p. Let me choose this. So I'm looking now on the probability that I'm closer than 1 over p in p's dimension to the surface. This is then 1 minus, just using this formula, 1 minus epsilon. Epsilon is 1 over p to the power p. Yeah, okay, but this here, of course, if p is going to infinity, this is an approximation for E, for the Euler number E, or for 1 over. For 1 over, because the minus sign here. Okay, so I mean 1 plus x divided by n. Let me go p. This goes to e to the x. Okay, so you have a minus sign. So this here is approximately e to the minus 1 for p large. Okay, and so this tells me approximately 1 minus 1 over e percentage of the volume is sitting in a small skin of my ball of size 1 over p. And so this here is approximately 1 minus 1 over e. 1 over e. E is 717 or 71, something like this. Okay, and so this here is approximately something like 62%, 0.6. So it's of this order. So this means, if I look on a neighborhood of 1 over p in high dimensions, then in this small, very small skin, I mean in high dimensions this is very small, about 60% of the mass are sitting there. Of course, if I take here 5 over, 1 over, if I'm going closer to 1, so I take 1 over 2p or 3p, then of course less and less mass will be sitting there. Okay, good. Okay, so that's somehow the asymptotic statements which we can make, but actually, I mean, very often we want more precise estimates. So, I mean, this is saying, okay, roughly, I mean, this is saying the probability goes to 1 and roughly 60% are sitting in the neighborhood of 1 over p. But okay, I mean, roughly, what does it mean? Okay, so at least in mathematics, we really want to make this roughly more precise. And this means we want inequality. So we really want precise estimates. How big is this probability? And so let us do this. I mean, just we have to read this. I mean, we have here a very concrete formula. So in principle, we know exactly what this is. But this here to the p is a quantity maybe which is not so directly clear. I mean, usually we want to have exponential estimates, and of course we can write this very nicely in terms of an exponential. So this is very close. But let us do this and then do precise estimates. Okay, yeah. And for this, yeah, we have. Let us use the following lemma. So essentially, we just have to compare this term here with an exponential term. And this, this is something which inequalities, which are used quite often. So let me write it down explicitly. Those are simple estimates, but they are quite useful. So for any p bigger than 1, and epsilon, of course, epsilon between 0 and 1. Usually we are interested in small epsilon. The estimates are true for all epsilon, but of course, epsilon bigger than 1 doesn't make sense because we are looking on 1 minus epsilon. Okay, so it's true for all estimates which we are doing, but of course, usually the epsilon is something small. Then it's really an interesting quantity. Yeah. So what do we have? So I just want to estimate this 1 minus epsilon to the p against an exponential function. So I'm estimating this against e to the minus epsilon p. Okay. So just that I write this term more in exponential form, in particular where the epsilon and the p are also coupled, where I see much better how they should go together. You see exactly. If I want to keep this constant, epsilon should be of the order 1 over p. Of course, here we also see this because we know this is an approximation for the e function, but here it becomes more explicit. Anyhow, and this is a precise estimate, and this is very simple. But still, let me say something about the proof. Essentially, of course, this is just taking the pth power of this estimate for p equal to 1. If I have it for p equal to 1, then if I just take the pth power, I get this one, because everything is positive. So it follows. So the only thing one really has maybe to think a little bit about is p equal to 1, but that's also more or less obvious. So everybody should be able to do this. So this follows from the obvious case p equal to 1. So where it just says, yeah, maybe I write 1 minus epsilon is bigger than 0, and it's less than e to the minus epsilon. So this is the case p equal to 1. Okay, and of course this is bigger than 0, so I can take the pth power of this, and the inequality here stays the same. Okay, and this is now a simple calculus property which you can, for example, see maybe if you just look on this function as a function in terms of epsilon, and you see how it behaves. So if you write this in epsilon, so we're looking from 0 to 1. 1 minus epsilon is, this is just this function, and this e function, this is the exponential function which comes from here. Okay, and then goes like this. And the derivative of this here is equal to 1. So here they are touching, but then I'm above. So you just can take the difference of this and see that the derivative is positive here. Okay, so this this should be clear. Okay, and so this is for p equal to 1, and the general we then get by taking the pth power. Good. Okay, so that's a very simple estimate, but let us see how we can now rewrite this formula in terms of this for precise estimates. And this here is a very simple situation where we have you have a very explicit, concrete formula which is very easy to analyze. Okay, for more complicated questions, of course, the formulas might be explicit, but more complicated, or even we maybe don't have really explicit formulas, but at least we can try to get estimates. So in here, everything is very explicit. And so let me just write down the combination of this and what we saw before. As a theorem. So namely, in the setting where where we have this, but that's exactly where we are interested. So for any dimension p greater or equal 1 and epsilon between 0 and 1, we have that the probability that my vectors in the unit ball in dimension p have a length which is bigger than 1 minus epsilon. Okay, let me write down again the exact formula which we observed here. So this is 1 minus epsilon to the power p. Okay, but now we can use for this the estimate. So this here is less or equal. So here I have 1 minus. So here I get the estimate in the other direction. So this here is greater or equal than 1 minus, the estimate which we have for this, which is 1 minus e to the minus epsilon p. Okay, so that's now really maybe our form of a concentration estimate which we want to have. So some properties concentrate. I mean, usually we have kind of exponential concentration. So where the dimension shows up in an exponential way, and maybe also how close we are should also show up there. So that's the thing which we want to see. And so in particular now, of course, I can also now make this with the 62%. Also write this as an inequality, and the probability for the vectors in a unit ball for which the length is bigger than 1 minus 1 over p. This can also be estimated, just by putting here epsilon equal to 1 over p. I mean, this is true for any epsilon. I mean, I can choose also epsilon depending on p. Okay, and I choose it as 1 over p. So if it is bigger than 1 minus 1 over e. Because if epsilon is 1 over p, I have e to the minus 1. Okay, so these are the 62%. Okay, so this, I mean, this only gives us one direction, so it says it is at least 62%. I mean, if you really want to have a more concrete, better approximation, you should also do an estimate in the other direction. But usually, I mean, with this estimate, we want to see that we are close to 1, that this goes to 0. So that's usually the direction of the estimates we are really interested in. Okay, of course, you can also try to think about estimates in the other direction so that you really know more or less exactly how much mass you have. Good. Okay, so that was maybe a very simple situation, but which shows more or less what we really want and how we are trying to do this. Okay, but now maybe let us look on a bit more interesting, also bit more complicated, but still manageable situation about the equator. So the second slogan which I had was that the mass concentrates close to the equator. Okay, so let us see how we can prove this, and let us also see what we really mean with this. Good, so let me maybe also just write down again the slogan, and then make this precise and try to prove it in particular. Almost all of the volume of the ball lies near its equator. Actually, there are many equators, and this is true for any of them, but maybe we should think about what we really mean with this. So what is the equator? So let us consider our vectors. So let us consider the vector, and as usually I denote the components of it by t1 up to tp. So this is my vector in a unit ball. And now equator is with respect to a chosen direction. So usually it's with respect to the North Pole. So I take the vector going the North Pole, and then the equator is essentially what is perpendicular to this. Okay, and so let us do this. And we choose here one direction. And let's say the North Pole there, that's the last guy here. So that's the guy which is the North Pole direction. And then perpendicular to this means that the last component has to be equal to 0. So we consider this. And we choose now. But this is arbitrary because we can make any choice but too explicit, and it doesn't depend which, I mean, the arguments don't depend on which choice we make. We choose a direction TP, the last component of my vector, as a direction into the north pole, no? As the north direction, which doesn't have a real meaning in higher dimensions, but just to compare it with maybe what we think of in 3 dimensions. Okay, and then we say the equator corresponding to this is the hypersurface which is orthogonal to this, but this just means that the last component must be equal to 0. So the equator itself, this is a p minus 1 dimensional object. So this is, those are the vectors in my unit ball which are orthogonal to this, but this just means that their last component is equal to 0. So I mean, for example, if I'm in 2 dimensions, then let's say the north would be this, and the equator would just be this line here. Okay, and in 3 dimensions, it would be the plane which goes through 0 and which is orthogonal to the vector pointing to the north pole. So this is north, and this here is the equator. Okay, and now we are saying essentially that most of the mass is, of course, not exactly on the equator, because this has mass 0. This is a p minus 1 dimensional object. So this is a p minus 1 dimensional region, because one of the components is exactly 0. Okay, so this doesn't have volume, at least not a p-dimensional volume. We are measuring everything with the p-dimensional volume. Of course, I could say it has p minus 1 dimensional volume, but that's not what I really want. I really want to have probability in my p-dimensional space. So I have to talk about the p-dimensional volume, and as before, I'm not saying exactly everything is on the surface, but it's in the neighborhood. And again, I can say here everything, or more or less most mass, is sitting in a small neighborhood of this equator, which means again I should allow a deviation of epsilon, maybe in plus and minus direction here. So I would require that the last component has absolute value less than epsilon. That's what I mean, that it's close to the equator. Good. Okay. So this is my thing here, and so now I'm looking on the probability of this. So the probability of being close to the equator is then, of course, given again. So again, I write it as a probability of okay, let me write it explicitly. The probability of the points in the unit ball in p dimensions, for which the last component is small. I mean, the other components I don't care, but for one component I want it to be small, and I want again to be smaller than epsilon. So I want that this last component is smaller than epsilon. Okay, and again I'm saying, mass mostly concentrates there, so I would like to see that this again goes to 1 if p goes to infinity. And of course, again, what do I mean with the probability? I mean the volume of the vectors which have this property normalized by the volume of the unit ball. So this is the volume of my elements in the ball, for which this Tp, okay, absolute value is less than epsilon. This means the Tp lies between epsilon and minus epsilon. Okay, and I have to normalize this by the volume of the ball. Okay, and now you see, of course, the volume of the ball we know, and here we have now to calculate something, elements, vectors in the ball with a given property. And again, this is more or less something which we can do, because, I mean, how do we calculate volume of such elements? We do iterated integration, and I mean here, okay, one component is restricted to the interval from minus epsilon to plus epsilon, but again, this is something which we can do very explicitly. Okay, so let me write this down. So this means, okay, if I want the volume of a set, I integrate over my variables, over my components, t1 up to tp. And here the last component is special. So namely this one, I only integrate from minus epsilon with plus epsilon, because that's what it means, that this tp is between minus epsilon plus epsilon. I should only integrate there. But the other guys, I'm integrating again over, I allow everything which is possible for the unit ball. But of course the condition now, maybe let me first write, of course I'm integrating over all my variables. So tp minus 1. And the last one is special. Maybe I just denote it by t. Okay, it's tp, but maybe I denote it by p. But now, so I integrate at the last about this one. And if this is fixed, the integration of the other ones, of course, has to satisfy this condition here. Or no, I mean, I still need the condition that I'm in a unit ball. And this condition is just that the sum of all the squares is less than 1. Okay, but if I'm fixing the last t, then of course the condition for those guys here is that t1 squared plus tp minus 1 squared. And now I would have plus tp squared is equal to 1. But in terms of those guys, I bring the last one on the other side, and I'm just calling it t. Yeah, or maybe I call it tp. So just okay, so I'm just writing it like this. Okay, and I still, of course, have to divide by the volume of this. Okay, and now you see, I mean, this integration over the p minus 1 first variables is now again integration over a ball, but now the ball of size 1 minus the square of the last coordinate. Okay, so depending on how I choose the last coordinate, I have to integrate over balls of varying size. Yeah, but balls, we know how to integrate. So what I really have here is the integral from minus epsilon with plus epsilon. So this integration over the last variable I leave open. And then doing the integration over the other p minus 1 variables, this gives me exactly the volume of a ball in p dimensions, but now the radius is 1 minus t squared. And okay, it should be the square root of this. And now I really rename tp to just to t, because now only one integration is left. So this is dt, and I have to normalize by the volume of this. Good, but again, yeah. Yeah, exactly, yeah. Very good, yeah, of course. Yeah, I have integrated here over p minus 1 variable, so I get here the p minus 1 dimensional ball. And you see, essentially, I mean, when we calculated the volume of the ball, we made a recursion where I integrated out two variables. So I compared the p-dimensional ball with the p minus 2 dimensional ball. Okay, and you see here, I'm just going down a step in one. You can also do this if epsilon is equal to 1 here, then essentially we are comparing here the p minus 1 with the p-dimensional ball. So also recursion where we compare dimension p and p minus 1 is also quite easy. So. Okay, and that's more or less what we are doing here now. Good, okay, yeah. And so, yeah, of course, so here, I mean, the radius here, the t, is varying, but we know how the volume depends on the radius. So it's just the volume of the unit ball times the radius to the power of the dimension, which here is p minus 1. So what I have here is then, yeah, it's the volume of the unit ball, which I can take out of the integral. And of course, it's the unit ball in p minus 1 dimensions. And I divide this by the volume of the unit ball in p dimensions. And then I'm left with the integral over the volume of the ball in dimension p minus 1 of radius square of 1 minus t squared, and this is the volume of the unit ball times the radius to the power p minus 1. So I have here the radius is 1 minus t squared to the 1/2, and I have to take this to the power p minus 1, and the 1/2 is the square root there. Okay, so that's what I have to do there. Yeah, okay, now again we have a very explicit formula. I mean, in principle we know those volumes here, we have the formulas for this, and of course this is also an integral. This is now going from minus epsilon to plus epsilon integral, which we can also deal with. Okay, and yeah, maybe I write down the formulas for the volumes. There, of course, we get now pi and gamma functions. And of course, I'm comparing here p minus 1 and p. So it's those constants, essentially constants depending on p, are not cancelling away, but that's essentially what I have to understand here. So, and maybe I can write it down. So what was the volume of the unit ball in dimension p? Yeah, so maybe let me write it down here. So it was pi to the p over 2 divided by this gamma function of p over 2 plus 1. So this was this kind of factorial. And here I have the same, where I have to replace p by p minus 1. So here I have pi to the p minus 1 over 2 divided by the gamma function of p minus 1 divided by 2 plus 1. Okay, and now of course I have a very explicit formula. I mean, I understand, in some sense I understand those quantities, and this is an integral which I can also easily understand. Okay, principle we understand it, but maybe now we should really try to make this precise understanding. And what I'm doing now is again looking on the asymptotic behavior. So as before, looking how does this behave if p is large. And of course, the statement is it should go to 1. That's what maybe we should see, and that's what I want to do in the following. And of course, for this, we can use, okay, I mean, this is explicit, the gamma function. This is of course a bit not so clear, but we have the Stirling formula, which tells us how this behaves for large dimensions, and we can use this. And this other integral we can of course also deal with. And that's what I want to do. Okay, and then, I mean, yeah, so essentially I want to do the asymptotic somehow of the first formula here in the case from before, and this estimate that we really make precise estimates, that's something which you are asked to do in the assignment. So that's really working with this example, making these asymptotic statements precise as inequalities. That's something you should do in the assignment. So I only want to do now the asymptotic behavior, which shows that it really goes to 1. So this is just the volume of those two guys. And then I still have here the integral from minus epsilon up to plus epsilon 1 minus t squared to the power p minus 1 over 2 dt. Good, okay, and now to see the asymptotics, let us use the Stirling formula, or maybe let us first look, okay, the pi's. I mean, the pi's are very explicit. Most of them cancel away. Here I have to the power p over 2, here to p over 2, and then I have a extra minus 1 over 2, so the square root, but with a minus, so I can bring this to the bottom. So I still have 1 over pi, square root of 1 over pi. That's what is left over of the pi's. And then I have the gamma function. Okay, now I bring it, the one on the very bottom, I bring to the top. So this is a gamma function of p over 2 plus 1 divided by the gamma function of p minus 1 over 2 plus 1. And then I still have my integral, minus epsilon up to plus epsilon 1 minus t squared p minus 1 over 2 dt. Okay, and now I used Stirling's formula. So this is approximately 1 over the square root of pi. And for the gamma function, the Stirling formula tells me, so that if I have an argument plus 1, then, yeah, what is it? It's the square root of 2 pi times the argument, which is p over 2. And then I have the argument divided by e. So the argument is here p over 2. and I divide it by e, and it goes to the power of the argument, which is p over 2. So that's a Stirling formula, which tells me how this behaves for large p in more concrete terms, which are easier to understand what they do. Okay, so that's for this guy, and then I have to divide it by the same kind of object, where I replace p by p minus 1. Okay, so here I have then 2 pi p minus 1 over 2, the square root, and here I have p minus 1 divided by 2e to the p minus 1 over 2, and the whole thing is still multiplied with this integral. Good. Okay, so what do I have here? Of course, I mean, a couple of things go away. I mean, the 2, so those go away. And also this here cancels with this. Okay, and then here I have the ratio of this with this, but this here is taken with the power p minus 1 over 2. This is taken with the power p over 2. And I want to bring them together, so I give an extra 1/2 power to this, so that they have the same power and I can combine them. But of course then I I have to repair this. But so let me write it down. So it's the square root of this. Then here I'm left with p divided p divided by p minus 1, the square root. That's what is left over here. And then here I'm dividing this with this, where I also take the p over 2 power of this, because then the 2e's go away, and I just have the ratio of p and p minus 1. So I have p minus 1 to the power p over 2, but I haven't making the mistake that I have taken the power minus I have an extra power 1/2 taken here to get the same power p over 2, so I have to repair this by multiplying with p minus 1 over 2e to the power 1/2. Okay, and then I still have the integral here. Yeah, good. Okay, and now let's see. So what, where can I see the asymptotics? Again, this is something which goes like an exponential, like the e function, because so this guy here, I mean, maybe I write it better as it's 1 divided by 1 minus 1 over p. So I divide by p, so I have 1 over this, and then I have this to the power p over 2. So I get essentially this to the power p over 2. And now you see again, this is again approximation of e to the minus 1/2. Okay, so maybe I have here p over 2, so maybe I should also write here 2 and here 2. And then this guy here is this guy, and then I get then this is approximately e to the minus 1/2. So this here is, and I divide it, so this is 1 over e to the minus 1/2. Yeah, okay. Good. I mean, all this is quite simple, but okay, just one has to do it and not getting lost in all the terms. So we have this, and this e here now goes nicely away with this one, because this is 1 over e to the 1/2. Here I have e to the minus 1/2, so this and this I can cancel. And then, so what is now left? So I still have this 1 over pi here. So it's 1 over square root of pi. Then I have, what do I have? I have here p minus 1 to 1/2, and I have here, this cancels this p minus 1 here, and I'm left with this square root of p here. Yeah, okay, and then I have the square root of 2 from here. So I have this 1 over pi square root of p over 2, and then I'm left with the integral. Oh, okay, so I mean this is essentially the only thing which is left from all these gamma functions and the pi's. Okay, and so I still have here minus epsilon to plus epsilon 1 minus t squared to the power p minus 1 over 2 dt. Yeah. Okay, and now what do we see? Okay, we still have to deal with this. And again, we should see here something which we can integrate, which we understand. And again, what we have here is essentially a kind of approximation of an exponential function. Okay, so how do we see this? Maybe first of all, I mean, I have here p and a p minus 1. Asymptotically, there's no difference. So asymptotically, I can also replace this here by the power p. Or you can say I replace this by the power by p minus 1, and then whether p is large or p minus 1 is large, it doesn't make a difference. So this is 1 over the square root of pi. Here I have p over 2. And then I have the integral from minus epsilon to plus epsilon 1 minus t squared, and I say this is now asymptotically the same as p over 2 dt. Good. Okay, and then if I have something to the power p, then here I should have something which behaves like 1 over p, because then I get an approximation of the exponential function. That was also the idea before. Such terms I control, but they behave closely to an exponential function, because this is somehow this formula 1 plus x divided by n to the power n. This behaves like e to the x. Okay, and this, in order to do this, I make a substitution which somehow writes this t here as something which also has this factor p over 2. So I'm substituting now t in the variable s, but scaling it with this guy. Okay, so for t, I plug in s divided by this, and then you see the t squared gives me then the factor p over 2 here. And of course, this changes the limits here. Okay, but that's okay, because I mean here I'm integrating over a small interval, which maybe it's not so clear how to control. If I'm changing the limits, then I'm making the boundaries. If I'm replacing t by s, then I will integrate here over bigger and bigger intervals, and essentially I will integrate over all of R, which I can control again. So let me now replace the variable t by the variable s, where I just the relation is that t is s divided by the square root of p over 2. So this here is now 1 over pi, and so I'm replacing t squared by s squared divided by p over 2. So it's p, and the 2 goes here. Then I have to the power p over 2, and the dt is now becoming a ds divided by the square root of p, and this actually goes nicely with this term. So this also disappears. So actually this times this is exactly the ds. Okay. So this goes away. And I have this here, and now of course also the limits here have changed. If t runs from minus epsilon to plus epsilon, then s runs from minus epsilon times this and up to plus epsilon times this. So here I'm integrating now from minus epsilon square root of p over 2 to plus epsilon square root of p over 2. Okay, and now you see if p is large, actually the limits go to minus and plus infinity. So actually I'm integrating more or less over all of R. Okay, and this here is now an approximation of the exponential function. More precisely, what do I have here? I have here p over 2, that's the exponent. This is showing up here. So this here is an approximation of e to the minus s squared. So this here is approximately e to the minus s squared. Yeah, okay, and this here goes to minus and plus infinity. So what I have here is approximately now the 1 over pi, the integral from minus infinity to plus infinity, e to the minus s squared ds. Okay, and now this is something which we know, or should know, or at least after you have done the next assignment, you have to know, because that's that's the first assignment. I mean that's of course the famous Gaussian integral. So this integral here is exactly is pi. So this here is exactly 1. Okay, and so you see asymptotically, if p is large, this really is close to 1. Okay. Yeah, but now you might say, okay, you have made many asymptotics, and maybe something is not clear, and maybe it's not clear how big the mistake is, and you are right. So we better should do concrete estimates, namely saying the probability that we are closer to 1 than something we should be able to estimate this in really maybe some exponential form or whatever, and yeah, you can do this in an assignment. So in principle, instead of doing these more asymptotic statements, one really can do real estimates. Okay, so let me write down what we have seen here, more or less, and then also let me write down the precise formula which you are asked to prove as an assignment. Okay, so here, from this, we have seen so this is for any epsilon bigger than 0. So epsilon was here fixed. And you see, I mean, okay, if epsilon is fixed, this here this was in the end it was only showing up here in the limits of my integral. If epsilon is fixed, then if p goes to infinity, I integrate over all of r. Okay, and so we have seen that the limit of the probability that Tp is less than epsilon, if p goes to infinity, that this is equal to 1. Okay, if we believe all these asymptotic things. Okay, but instead of believing, maybe we should prove it really, and that's what you have to do. So what one can show by more precise estimates we can also control the speed of the concentration, control the speed of concentration in the following way. So namely, we can show that the probability that Tp is less than epsilon, it has to go to 1, but we can be more precise. So namely, it is bigger than 1 minus, and now good, there should be a term which goes to 0, but this we can write explicitly as e to the minus p minus 1 over 2 times epsilon squared. Okay, times 2 pi. Okay, so you see, yeah, exactly. So this is not only true for one equator. So here I could also say, instead of Tp small, we could also say Tp minus 1 small, the same argument, or T1 small. So we could have those p equators. And for each of them, you have an estimate like this. So most mass is sitting there. And from this, you can then say, if you take the intersection, then it's also close to 1. Mind me, because if you have a finite number of sets, each of which has a volume or probability which is close to 1, then the intersection of them is still close to 1. A little bit further away, but I mean you are exponentially close. So if you take a finite number, you're still exponentially close. Okay, so for any equator, and there are many more, not just the p, but you can take vectors which are showing in any strange direction, in any direction. So for each of them equators, you can do this. So for each, so the mass concentrates in all of them, so it also should concentrate in the intersection of them. Of course, I mean, if you take the intersection of infinitely many, then such things break down, because I mean, you can have for infinitely many things, you can have concentration for each of them, but if you then take, let's say, exponentially many of them, then you are losing the concentration. But for any fixed number, you can take 1,000 equators, and then it's still, the mass is actually sitting in the intersection. This makes it, in small dimensions, this makes it even stranger, because in small dimensions, you have the feeling nothing is, or almost nothing is sitting there. So I mean, one equator, okay, that's the equator, but then if you take the other equator, but the intersection of this is just very small spots. But in high dimensions, this is still very big. So essentially, okay, maybe, yeah, so what are we saying here? I mean, we are saying that most vectors in a unit ball have the last component quite small. Okay, and maybe we can also do it the other way around. What is essentially, what should be the size of the component? So it's again, I mean, in order that this is not so small, how should we choose this epsilon such that this here maybe is a finite value? So how should we do this? So this is, I mean, this inequality is essentially also showing us how we should scale epsilon with p. So namely, how should we do this? This guy here should be constant. So epsilon should go essentially like 1 over the square root of p. Okay, so this is telling us that most vectors in a unit ball have a pth component which is of the order 1 over square root of p. Okay, and it's also saying us, okay, most vectors have a first component which is of the order 1 over square root of p. And they also have a second component which is of the order square root of p. So this means essentially all components are of this order. And if you said it like this, maybe it's not so surprising. I mean, we are saying here, okay, the first component is of the order square root of 1 over p. And then we say the second component. But if you now say both components should be of this order, it's the intersection of the two conditions, but still, this looks more plausible. So maybe from this point of view, the whole thing is maybe not so crazy. Good. Okay. Yeah, but it's so you see, it's mean high dimensions. Concentration is okay. Slogans are nice, and you can also asymptotically understand it somehow. But without precise estimates, it's easy to fall into traps. Yeah. So even I don't really have a good picture of what really happens in those high dimensions. So good. Okay. So, but let's see. Yeah, but in the assignment, I mean, you will prove this, and then maybe you can try to think more about it if you add more conditions or so. And maybe actually, okay, so we still have the next slogan, which goes a little bit in this direction, because there we are, yeah, looking on two vectors. So it's getting a bit more complicated again. Okay, so the slogan is most vectors are orthogonal. So this means I should take two random vectors in my unit ball, and then I should estimate the probability that they are close to being orthogonal. Of course, it's again close. I mean, of course, exactly orthogonal is again a situation which has zero probability, but being close to it. That's again where we say this is has quite high probability. Yeah, okay, so I consider two vectors, x and y, in the unit ball. And now the question is, what is the probability that they are close to orthogonal? Good. Okay, so I want the probability of two vectors in a unit ball, and of course I have to measure the closeness to orthogonality, and for this I can essentially take the inner product, because this essentially gives me if I normalize it, the cosine of the angle between the two. Or I mean, if the inner product is 0, this means they are orthogonal. So being close to orthogonal means the inner product should be close to 0. Okay, so I'm looking on the inner product. Okay, but of course, I mean, the inner product can be small because the length of the vectors is small, so I should normalize it, because then it's really the cosine of the angle between them. So I take the inner product, but I normalize it with the length of the vectors, and then I ask that this should be less than epsilon. So what is the probability of this? So can we estimate this? So the idea is, again, this should be, the probability of this for any epsilon should go to 1 in high dimensions. Okay, but now of course it's again a bit more complicated. So in particular, we are not talking about one vector, but I'm talking about two vectors. And of course, in a sense, we are talking about independent vectors. So I take two vectors. So what I really talking here about is the volume, let's say, of a pair of vectors, and they are living in the unit ball times the unit ball. I mean, I just take a pair of elements in the unit ball which satisfy this condition, and then of course I have to normalize it now with the volume of taking all pairs. So this is the volume of taking just a pair of vectors from the unit balls. But of course the volume of such a product is just the product of the volumes. So I mean the volume of a pair. This here is the volume in a p-dimensional space. If I take the volume, if I have two vectors in R to the p, I just put them together and I have a vector in R to the 2p. And of course the volume of this pair is just the volume of the product of the volumes. Okay. And okay, maybe it's not so clear how do I calculate here with two vectors and calculate it's a set of vectors with a condition, but because the whole thing is symmetric, as we said before, as before, it doesn't matter which vector I choose for the equator, it's here the same. If I want to see what is the canonical relation between two vectors, this doesn't depend on, let's say, the first vector which I choose. So I take just one vector, and then I'm just asking how are other vectors sitting with this one? Because the whole thing is symmetric, and I can rotate everything. It doesn't matter which I take as the first vector. So this here is actually the same as fixing one vector here, let's say the second vector, and then just ask about the probability that the first vector has a small inner product with respect to this one. So this is actually the volume. I'm just asking about vectors x such that x and y has a small angle between them, less than epsilon, where I'm fixing this y, and it doesn't matter which y I choose. And I normalize this. So essentially for each y, I get the same volume here, and then I'm normalizing it by those volumes. So the volumes of the y's is just going away, and I'm just left here with dividing by the volume of the unit ball for the x's. Okay, so this is true for any fixed y in the unit ball. Okay, so this is somehow reducing the question again just to a question about one vector. So it's a priori question about two vectors. I should choose both vectors randomly, but essentially it doesn't matter which I make a choice for the first one, and then the answer for the second one is always the same. The probability that it's small is always the same, independent of which I have chosen for the first one. So I can just fix the first one and just calculate the probability for the second one. That's what I have written here. So in principle, the original problem would be calculating like this, but because of the symmetry of the problem, I can fix the y arbitrarily and then just calculate this. And now, fixing it arbitrarily, I can essentially go back to what I did before, because the inner product, I can, for example, I can calculate this very easily if I choose as my vector y a vector which has only a component in the pth direction, because then the inner product is just looking on the pth component of the vector y, and this is exactly the problem which we solved before. So in principle we can go back to what we did before. Okay, so it's the volume of this, and so for any y, and now I make a smart choice. So namely, I take for y the vector where all components are 0, but the last one, so this is a vector in the unit ball, so that's okay, and it also has norm 1, but in particular it has a nice property that the inner product of this vector with another vector just gives me the pth component of the other vector. So this means the probability now, what I have here, so this divided by this, so this is the probability of my vectors t1 up to tp in the unit ball, for which this inner product is less than epsilon, but the inner product between x and y is the pth component. So this is Tp, but then I also dividing by the norm of y, of the length of x and the length of y. Y has length 1, so this goes away, but I have to divide by the length of x. So it's close to what we had before, but now the length of x is also showing up. Namely, this has to be less than epsilon. Good. Okay, so you see, I mean, we have somehow the problem for controlling the angle between two vectors. We have reduced this essentially to controlling for one vector its last component, but also its norm. But for both of them we had concentrations. We know this here is small with a high probability. We know this here is close to 1 with a high probability. So hence essentially we have to combine those two things which we did before to get this estimate here. Okay, and essentially, I mean, we get something for this and something for this. We should control both of them so that the combination here gives us the epsilon. So maybe it's good to define something for which we control the pth component and the norm, and let me call this eta. And I define this by saying that eta divided by 1 minus eta should be equal to epsilon. And then I will control this and this in terms of eta, and then control of both gives me exactly this epsilon. Okay, so it just makes it easier. And you see, I mean, epsilon small will mean that eta is more or less the same as epsilon. So eta will be more or less the same as epsilon, and 1 minus eta will be equal to essentially 1. So for small epsilon, I mean, that's the situation we are interested in. Eta and epsilon will be more or less the same. Okay, but it's good to define this, because then we can use this eta for controlling the pth component of our vector and also controlling the norm. And there we had statements. So we had this statement here. Maybe I should leave this one. And we had before the one for the norm. So what we know is the probability that the pth component is less than eta. So now I'm writing it down for eta. That this we could estimate by bigger than 1 minus, I mean, this is exactly what I have here, now just eta instead of epsilon, is 1 minus the exponential of minus p minus 1 over 2 eta squared times 2 pi. And we had also that we can control the norm. The norm is close to 1, so namely that the probability that the norm is bigger than 1 minus eta, this was larger than 1 minus epsilon minus p times eta. That was the first thing we did. Good. Okay, and now we just combine this. Essentially, if we want this, then this can be guaranteed if we have this and this together. Because if I have this and this, then we get exactly this. So maybe let us just write down this first. I mean, that's the reason that I introduced this eta, because if I have those two for eta, I get this one for epsilon, if epsilon and eta are related like this. So this means if I know that Tp is less than eta, and if I know that the norm is bigger than 1 minus eta, that's what I have written down here, yeah. Then from this, of course, it follows that the ratio of Tp divided by the norm, I mean Tp, so this is less, I want to estimate in this direction, this is less than eta, and this here is bigger than 1 minus eta, so if I divide it, again, it goes in this direction, less or equal, so it's less or equal to 1 minus eta. Okay, and this, of course, is, I defined eta in such a way that this is equal to epsilon. So this means if I have both those properties, I have exactly what I want for eta. Okay, and I know the probability of having this property, this is close to 1, the probability of this is close to 1, so the probability of having both is also close to 1. That's more or less what also came up before. If I know a probability for one condition, I can also estimate the probability for several conditions. That's, I don't know how it is called, sum rule. So yeah, maybe let me write it down. So just to be very precise on this, because this is of course a very basic estimate. It's essentially just saying that the probability of the union of two events is less than the sum of the probabilities for them. But here it is written the other way around by taking complements and the intersection. So maybe that's one of the basic estimates in this context. So instead of saying that the probability is bigger than 1 minus alpha, I can say the probability of the complement is less than alpha. So this means what I have there is essentially saying I have the probability of the complement of some set is less than alpha, and I have the probability of some other set, the complement, is less than beta. So alpha would be this exponential in the first, beta would be the exponential in the second. And saying that this is less than alpha is saying that the probability of A is bigger than 1 minus alpha. Okay. Yeah, and then I can look on the union of AB, the complement of this, because this is the intersection. I mean, this will be the intersection of this and this probability. Okay, but no. Okay, no. What I want is the intersection. I want the intersection of A. I mean, A is really the set which I'm interested in, but I'm just writing the above equation in terms of the complement. Okay, so what I really want is the intersection, that I have both properties. But of course, the complement of the intersection is the union of the complements. And now, of course, if I have the probability of the union of two things, I mean, if I have the volume of the union of two sets, this is in any case less than the volume of the probability. This is the sum of them. So this here is smaller than the probability of A complement plus the probability of B complement. That's just, I mean, that's just the basic property of the probabilities. If I have two sets, probability of the union is smaller than the sum of the probabilities. Okay, and so this tells me, okay, and this here was by my assumption less than alpha. This here was less than beta. So this tells me that the probability of the complement of the intersection is less than alpha plus beta, or maybe if I really then go back to the probability of the intersection, if I'm interested in this, then this is 1 minus the probability of the complement, and so this is then bigger than 1 minus alpha plus beta. And of course this here was just the probability of A is bigger than 1 minus alpha, and this here was that the probability of B is bigger than 1 minus beta. So if I know that this here is closer than alpha to 1 and this is closer to beta to 1, then I know the intersection is at least closer than alpha plus beta to 1. So it's a little bit worse, but not too bad. If alpha and beta are small, alpha plus beta is still small. So that's the kind of inequality argument you use if you want to talk about having not just one property, but several properties at the same time, talking about intersection of events. Okay, and that's, if you use this, then this tells us that if I have the intersection of this here, then I will be in this set here. So this means the probability of this set here will be in any case bigger than what I get from the intersection here. So this tells me that the probability that I have, the probability, okay, in this, let me say it here like this, the probability that both, that Tp is less, the pth component is less than eta, and the norm of x is bigger than 1 minus eta. So this is by this argument then less than 1 minus, and now I have to subtract the two terms which I had for each of them. So I have to subtract 1 minus the first term, exponential minus p minus 1 over 2 eta squared square root of 2 pi. This is the alpha, and then I also have to subtract the other term, exponential of minus p eta. Okay, and the probability in which I'm interested, this probability, this is bigger than this one. Because whenever I have those two conditions, then I also have this condition. So here I have possibly more vectors which satisfy this. So the probability is bigger, but at least it's already quite big if I just take this intersection. Good, okay, yeah, so that gives you the idea. And of course now you see, I mean, this is a bit complicated. Of course you could now try to make an estimate which combining those two, but maybe that's really what you see. And essentially you see, I mean, for this estimate, if you want to be of some fixed order, eta should go like 1 over the square root of p. Here it should go like 1 over p. So this means for high p, one of the terms will be the dominating one. Yeah? Yeah, you're right. Yeah, because otherwise it would say the probability is smaller than something which is close to 1, which is not a very useful property. So this is something which should be small, and we want to see that we are close to 1 with this. Good, yeah. Okay, so are there more questions? So I hope this has given you some idea what, I mean, first of all, what we mean with concentration, how we precisely formulate this, but also how we can prove it. Okay, this is really basic calculations which show quite a bit of the tools. Okay, and so in particular in the assignment, you will be asked to show the first estimate. Okay, I mean, starting from the formula which we had there, we had a precise formula for the probability that the pth component is less than eta, but you should massage this in a way, in this estimate-like way. And there are hints, hopefully, enough hints so that you can do it. So it's on the same kind of level as here. Maybe technically, yeah, you have to know what you should do, but there are hints which tell you hopefully what you should do. Good. Okay, so that's about the volume stuff. And then the next thing we will look at is that we now, instead of looking on vectors which have a uniform distribution on sets, in particular on a unit ball, we are going to vectors which maybe are more popular and more interesting, namely Gaussian random vectors. So next time I will first recall a little bit what Gaussian random vectors are, and then we are trying to do the same kind of things, namely getting concentration for them. They also satisfy concentration. So if I have Gaussian random vectors in high dimension, they also concentrate at the surface of a given ball, which is maybe even more surprising than for the unit ball, because the Gaussian distribution has a distribution which is spread out over everything. Good. Okay, but I will do this next time. So that's it for today.